that they scatter the light, okay? So, light comes in, and if you notice on this one, I've given you that the focal length is 40 centimeters. So let's start with that idea. Focal length is 40 centimeters. Is that going to be a positive or negative number?
Negative.
Negative. Why? Because when that hits that light's going to get spread out. Okay? And it doesn't make any difference where the image is. On one side of it doesn't make any difference. Okay? So on a concave lens, the focal length in terms of calculations is going to be a negative value. Now, in this situation, I tell you that the object is at 20 centimeters. Okay? So in this situation, my object is inside my focal length. Okay? And there's nothing magic. Don't say, oh, the object always has to be outside or the object inside. It can vary. Okay? It doesn't always have to be, hey, in this situation. I just said, hey, here's the focal length. Your object distance is going to be 20 centimeters. Now, with these, this is why, when you notice on that diagram that I gave you, notice that some of the lines are solid and some of the lines are dashed. Okay? So what the dashed lines are showing is light that's either being reflected back or being refracted. Solid lines are showing the actual path of the light. So, if you look on this one, so you've got a line coming in and like this, so it's going to come off here, and it's going to hit that lens, and then it's going to try and get sent out in a direction away from there. So it's going to get sent out like this. Now, this particular line is going to try and go back through that focal point. Okay? So, it isn't just, oh, it's a random line that you draw. So, if you're actually drawing this, start at the focal point, go up to where it's going to hit the center of the lens, continue that back, and then draw that like this. Now, what that tells me, again, I've got this narrowed down. So what that tells me is that image is going to be somewhere in this region, okay? Because that's what happens with concave lenses. So I know this is going to be somewhere in here. That doesn't tell me where it's at, but at least now I have an idea of where it could potentially be. Now, here's the other thing. Since it's going to be in here, and this is like the top of the arrow, since it's got to be in this region, and that line is representing the top of the arrow, is the image is going to be upright or going to be inverted? It's going to be upright. So right now, I'm going to have an upright image. Since this is where this is going to be, do you think it's going to be virtual or real?
Has to be virtual.
Has to be virtual because of the fact that it's going to be basically appear as a hologram, which is what I just showed you guys back there. Okay? So it's going to appear as this floating little image in the sky. So that's my first ray diagram. Now, my second one is going to come through here, and it's going to go through that middle. Now, the odd thing about this one is that it actually kind of refracts back on itself. So it's going to go, start up there, it's going to go through the middle of that lens, and then it's tough to see because you're basically drawing a dashed line on top of the solid line. But this line, in effect, if you think about it, is going to come back like this. Now, at this point, I have the two lines meeting. So at a minimum, now I've got, hey, now I can kind of figure out that that image is going to be right there. Okay, so those two just kind of give me an idea that says, hey, this is what we got going. Now, if you look at what else could happen, so if in terms of like another focal point over here, so because there's going to be two focal, I've got this way out of proportion. You got another focal point over here. So to establish that third one, then if you come back from that focal point where it's going to hit this, so it would be coming in here like this, and so that's going to refract back and get this one. The third line on this one is really, really tough to figure out because of the fact that you have so many things that are crossing over. Usually on this one, because you know that's where it has to be, you can usually just get by with two lines, okay? You normally don't have to draw the third one on this one because that's the only place that this could be. Now, most importantly on this one is the math. So you've got a focal length of -40 because that's going to get floated out. So on the math, you have 1 over f minus 1 over so equals 1 over psi. So I've got 1 over the -40 minus 1 over 20, and then I'm going to take the inverse of all of that. So what do you get out of that?
-13.3 centimeters.
-13.3 centimeters. Now, that matches our very crude diagram, okay? Because the focal length is out there at 40. The object was at 20. We have an image inside of our object distance. Hey, that fits. It's cool. Now, based upon a very crude diagram, do you think your magnification is going to be bigger or smaller than 1?
Smaller than 1.
Smaller than 1. Do you think your magnifications, based upon psi and so, is going to be a positive or negative number?
Positive.
Why?
Because
You got an upright image. Okay? So, if you look at magnification, okay, let's look at magnification. So, because of this, in terms of, this is why it's handy to have, in this situation in particular, that negative psi over so. So I got negative psi over so. So my image distance is going to be a negative of a -0.3 centimeters divided by my object distance, which is always positive. Okay, you don't have to guess on that one. So my object distance was 20 centimeters. Now, your magnification is going to be a positive number less than 1. That's why we've got that small little upright image. Now, what you cannot tell by the sign of magnification is whether it's real or virtual. The only thing you can tell from magnification is it upright or it is inverted, okay? The sign of these numbers does nothing to tell you real or virtual. It can tell you where it is, it can tell you if it's upright, it can tell you if it's small, big, whatever. But what it cannot tell you is if it's real or virtual. That just has to come from the diagram itself. So what do you get for your magnification?
0.67.
0.67. Notice that that is less than 1. That matches with the diagram. Okay, cool. Nice. 0.67. So, in this situation, my object height is 2 centimeters. So, what that means is, so I take my magnification times my I get high. Which sounds really weird. So, if I take 0.67 times 2, you get 1.3. Okay? Notice that that is less than 2.
My sanity.
Huh?
My sanity.
Your sanity's fine. Okay? This is one of the weirder ones, okay? In terms of like practical, this works beautifully mathematically, but it's really tough to actually see this in reality because it's like a hovering value. Now, let's talk about the mirrors, because those are the ones that impact you, your daily life the most, especially if you have a cosmetic mirror. So, flip this over to the other side. So, we're going to quickly hammer through the two concave mirrors. I can promise you now, here are the ones that are asked most often. The concave mirror, the convex mirror, and the concave, or the convex lens. The convex lens and the two mirrors, in terms of reality, that's what impacts you the most. So that's what we're going to spend most of our time on. That's where most of the questions are going to come from, because that's what you use the most. Okay, so let's talk about that first one, top left corner, okay? So when you're actually drawing these, Charles, always start with your central, called your optimal axis. Always draw that first. Okay, good. Now, in this situation, you have a concave mirror. Is the light going to get gathered, or is the light going to get spread out?
It's gonna get gathered.
It's going to get gathered. So what's the sign of my focal length going to be?
Positive.
Positive. So I know, and again, there's no conditions to this. There's no conditions that says, oh, it's positive if you're inside the focal length, if you're outside the focal length. There's no conditions to this, okay? No matter what, your focal length is going to be a positive value. Doesn't matter where anything is. Your focal length is going to be a positive value. So if you look on this one, I've given you a focal length of 40 centimeters, okay? There's your focal length. And in this situation, your object is also at 40, okay? So it's rare that this happened, but it just made the geometry work out, and especially in the space that I had to draw this image, that's why I picked this. So in this situation, my focal length is going to be 40, and my object distance is also going to be 40. Now, here's the deal, okay? When you begin to draw the ray diagrams for mirrors, let me tell you the first one that you always draw, okay? And there's no exceptions to this. This is the first one I always draw. So you measure whatever that height is based upon your scale. And you can have different scales. You can have a different scale for the object in the image and a different scale for what's happening along your optimal axis. Yes, Connor asked.
Jacob was wondering, since we're doing the top left one, shouldn't F be 20?
Oh, it is focal length is 20. My bad. I misread that.
Jacob says you're welcome. Thank you.
What?
Are you trying to shove words into Jacob's mouth?
Whichever one doesn't get Connor B.
Yeah, that.
Yeah, I even had that written down. Focal length is 20. Okay,
Yeah.
back to our story. So here's the first one that you draw. So you take this line through that central optimal axis, wherever that object is, and you draw a line that's going to hit that center, right there. Okay, so the first line that you draw. Now, you make it symmetrical on the other side. So if this is like 1 centimeter high, you come down 1 centimeter here. If that's 1.5, you come down 1.5. You make it completely symmetrical. So if whatever that distance is whatever this distance is going to be, and then I'm going to draw that line like this, and then I'm going to take it out like this, okay? So here's what this is going to tell me, is that as soon as I get this line established, I know one of two things. It's either going to be here and inverted, or it's going to be on the other side, okay? Those are the only two places this can be based upon that one line. So this is why this is so critical. So you take that first line, you draw it here, hit the middle. I don't care what this is, okay? Doesn't make any difference. But whatever that distance is up there, you make it that same distance down here. You go from that center back out to that point, okay? That is the most critical line that you, and it doesn't make any difference. Convex mirror, doesn't make any difference. With mirrors, those are the first, that's always the first line that I draw. Start at the center, hit the middle, boom. There you go, you're off to the races. And at least tells me where this is going to be. Now, with this one, because of that focal length, then I'm going to draw another one that's going to come here, and it's going to hit. Now, this is actually parallel with this axis, okay? So this is going to come off the top. Mine's a little bit lower than that. But it's going to hit this, and then it's going to go through that focal point. So then it's going to come down here like this, and it's going to go through that focal point. Now, at this point, now I've narrowed it down. So where these 2 points cross, this is going to tell me where this might be. Now, I could take this line like this all the way up like that. But why, in this situation, is that going to do me physically? Why would that do me no good in terms of trying to figure out where the image might be on the other side of the mirror?
Because the two dots
Not gonna cross.
Those lines are not going to cross, okay? Those lines are not going to cross. So right away I'm going, okay, that won't do me any good, because if those lines don't cross, I can't form an image. So right away, I've got a pretty good idea of where this thing is going to end up, okay? And again, this is why I'm going off the top. So right away, based upon those two, I've got to figure, hey, my image is going to be flipped over. Now, notice on this one, I've drawn these as solid lines. On this side, I've drawn it as solid lines because the light's hitting and it's going in this direction. Notice on those, I drew those as dashed lines because they're there, but they're in the opposite direction that the light is going. Okay? So these are solid, that's the actual path of the light. Those are dashed because that's going on the other side. Now, if you do the math, my focal length is 20, so that's going to be 1 over 20 minus 1 over 40, and then I'm going to take the inverse of that to get my object distance, and trust me on this one, if you do this, you get 40 centimeters. That's where it ends up being at that same point. The object was the same, not the focal point. Now, so let's talk about magnification. Based upon this diagram, should my magnification be a positive or negative number?
negative,
Why?
because the negative side or so it's going to be both sides are positive.
No, but beyond that, look at the image. What's the image? Is it upright or is it inverted? It's inverted. Oh, I should end up with a negative magnification. So, if I take negative 40 over 40, I get,
Negative 1.
so that tells me that my image is the same size as my object, but it's inverted. Okay? Now, real or virtual? Sydney?
Virtual. Real.
It's going to be real, and here's the reason why. That light is going to be coming off here. I can put a screen there and capture that light. That's what I did yesterday. Remember yesterday when I had the split screen? And that light bounced off and I could project it on that screen, okay? So this one is actually going to be a real image, but it is inverted. Now, in terms of a cosmetic mirror, this won't do you any good, okay? Ladies, do not buy this as a cosmetic mirror. Why?
I don't wanna see myself upside down.
Yeah, and you're not going to get any magnification. So, great, I'm going to look the same size as I normally do. The only thing that's going to happen is that I'm going to look upside down. So I'm going to try and put on mascara in an image that's upside down. Cool, getting ready for the big homecoming dance Friday night. Okay, great. I'm trying to put on my false eyelashes and I'm upside down. That's cool. Okay, I'm just saying, hypothetical. Okay, now, here's what is going to play out in terms of a cosmetic mirror. So the next one, same idea. Same convex lens, but now my focal length is going to be 40 centimeters, and my object is going to be 20. Notice on this one, I'm inside the focal length. On the other one, I was outside the focal length. So in this one, my object is inside the focal length. So, again, start with the first diagram. So, come in here. I'm going to go like this. Sometimes I hate technology. This is one of them. Okay. So I'm going to draw this. Imagine that this hits the top of the arrow. In reality, it doesn't hit the top of the arrow. Then I'm going to flip this over to that exact same distance, and then I'm going to take this line and take it out like this. So I'm going to take this line so that that's symmetrical, and then I'm going to take that line out like this. Now again, at this point, I know one of two things. Either the image is going to be here, or the image is going to be over there. If the image is on the other side, will it be upright or inverted?
It has to be upright.
It's got to be upright, because this is what you're going to see is that arrow, the top of that arrow. So it's going to be going up like that. So it's going to be going up. So if it's over here, it's going to be upright. If it's over here, it's going to be inverted. Now, the next one I'm going to draw is going to go through that focal length. So I'm going to take this line like this. Boom. Parallel with that axis. And then it's going to go through that focal length. And then back out like this. So now, based upon those two, what are you going to see? Upright image that is
Enlarged.
enlarged. Do you think that's something you want in a cosmetic mirror?
Yes.
Yes. I don't want to see my pores upside down. So this is going to be cool. But you have to be inside the focal length. Now, even though my focal length is 40 and my object is 20, is the focal length in terms of calculation still going to be a positive number?
Yes.
Yes, because it's still bringing the light together. So, in this situation, I'm going to take 1 over 40 minus 1 over 20. So I'm going to take 1 over 40 minus 1 over 20.
Wait, isn't that the
Negative
same sort of 40 centimeters?
What'd you get?
Negative 40.
Negative 40 centimeters. Ooh, so what that means is that this is going to be where that second focal length is on the other side. So, here's the deal. I've got a negative image distance. So what do you know about the sign of my magnification?
It's positive.
Oh, now my magnification is going to be a negative of a negative 40 centimeters over,
20 centimeters.
I get
2 times magnification.
a positive 2 magnification. Why is that? There's 2 reasons, no pun intended, why that's a good thing for a cosmetic mirror. You're going to get an image that is
Upright.
and magnified. Okay? It's like, whoa, now I can put on my eyelashes. Cool. Okay? Because it's going to be upright and magnified. But you have to be inside the
Focal length.
focal length. So this is what makes concave mirrors unique. You can produce upright and inverted images. You can produce magnifications that are bigger than 1, magnifications that are less than 1. That's why I had you hold those points out there. Now here's the last one, and this is the easiest mirror, and that's a convex mirror. So the beauty of convex mirrors, that was horrible. The beauty of convex mirrors is that there's no guesswork to it, okay? They're always going to be the same. So, again, if you look on this one, I told you that, and this is like that one that's just below that. So, you've got a focal length of 20 centimeters and an object distance of 40. So I'm going to put this arrow up here. So the beauty of this is why I say this will last, because this is actually the easiest one, because those are the fewest variables. So always start with that first one. It's going to go through, hit that. I'm going to bounce that back like this. And then I'm going to continue this on. So the beauty of convex mirrors is that you only get images that are on the other side of the mirror, okay? There is no, oh, is it upright, which side's it on? Convex mirrors only produce images that are on the other side, okay? That's it. You don't have to think. So the next one is that I want to go parallel with that optical axis. Okay, and then it's going to hit that, and then it's going to try and go through, there's a matching focal length over there, and then it's going to try and go through that focal length on the other side. So now I've got this. So right away, based upon those 2 lines, what do you know about the image?
It's shrunk.
It's upright. What's my magnification going to be?
Less than 1.
Less than 1. Okay? So this is why when you took that mirror and you were looking at the convex side, you look small. But you never flipped over. Okay? Because of the fact that either you can only produce an upright image on the other side. Now, because this is on the other side of the mirror, do you think that's a real or a virtual image?
Virtual. You're not
Virtual.
projecting it
I
on
can't
screen.
project that. But here's where this gets wonky. What your eye sees, okay, in terms of this, what your eye sees is the light that's being reflected off of it, okay? So we talk about the image being on the other side, but when you hold that up, it's light that's going to hit, diverge, but it's still going to hit your eyeball. So if you do the math, I got a focal length of 20. Is this going to be a positive or negative focal length?
Negative.
Why? Divergent. So this is going to be 1 over negative 20 minus 1 over 40. You do the inverse of that, you get negative 13.3 centimeters. Now, this should all make sense at this point. When you do the magnification, you're going to take a negative of a 13.3 over 40. What's your magnification going to be less than? 1. Oh, you're going to see something small. Is your magnification going to be positive?
Yes.
Why?
Because the image is upright.
Because the image is upright. There you go. Once you see the pattern, it's not bad. And just a matter of seeing the pattern. Okay, so. Good news is you don't have to take the book home. The bad news is.
I hate
David, right?
Okay, so let me quickly get you started on this. And pay attention to what I want in terms of the spirit of this assignment. So I gave you different things: carrots, candles, cosmetic mirror with a brush, a light bulb, okay, a bicycle. You have different things. I'm really not going to grade you on your artistic ability to draw these things, but it was just to kind of break it up. So here's what I want done. So in the spirit of this, and there's only 5 of them that you're actually going to have to draw out. So in big bold letters, I tell you, I want the object labeled, the image labeled, the image distance, the focal points, and the scale. Okay? So you got a carrot is placed 30 centimeters in front of a converging lens. Is the 30 centimeters your object distance or your image distance? Or your focal length? Object distance. Obviously, I tell you the focal length is 10. So not in here. You do not have enough room to draw these here. On another sheet of paper, you are going to choose a scale. Like you got 30 centimeters. What I would do, I maybe maybe I'm going to let 3 centimeters equal 1 centimeter. Okay, hey, there's going to be 10 centimeters. Okay? That's what I want to see. And then you're going to go, oh, okay, right. The carrot is placed in front of a converging lens. So I got this action going on. And then I've got my carrot out here. Okay? And then I've got a focal length of 10. So here's my focal points. Here's my object. And by the way, I get the most difficult one out of the way first. Okay, the rest of them are easier after this because this is this converging lens. I'm sorry, it's a converging lens. I was looking at this one. It's a converging lens, okay, like this. So I lied, I give you the easiest one first. So this is going to come in here, it's going to go like this. Boom, this is going to go like this. This is going to hit this. Boom, go across. You're actually, yes?
Would graph paper work too?
I would use graph paper if I were, when I did it, I'd use graph paper. That's what I would recommend. So here's the spirit of this. You are going to use, this is no math calculations. The spirit of this initially is that you're going to use your ray diagrams to figure out these numbers. Okay? And I know there's going to be some variance. Now, when you get to the next set, that starts at the bottom, then I tell you, now use the thin lens equation for each of the preceding problems to calculate the actual image distance. So the spirit of how I wrote this was that you drew the diagrams first, then you do the thin lens equation to go, wow, was I close? Like, oh man, that was a train wreck. That sucked. I did something horribly wrong. Okay? That was the spirit of that. Now, yes, there is a back side. Notice on this, though, I tell you on the line provided, make a sketch. Okay? These, you don't have to draw them to scale. You're just going to make a sketch. And then you're going to do the math to figure out the actual image distance. Tell me, is it upright or inverted? And the magnification. Okay? So this one, the image, the sketch is just to say, hey, can you prove to me that you actually understand what's going on? Then, but this on the back side, those do not have to be to scale. They're a sketch. but I at least want the object labeled and the image labeled. On the first diagrams, you have to label a whole bunch of things. All right, I'm done. You're on your own. Good luck.
It's not that bad. I just don't want to spend the time to do it.
If you want graph paper, I think there's a stash in the back there.
I'd like 3.
That's might be true most of the time, but that isn't like an absolute
I'm already back in my seat. You good, Danny? Oh, way back. I am tired after this lesson.
I took a nap during this lesson. I will be watching it when I get home. Okay. You have to think about it in like the terms of like the actual the previous lesson. Like bends as it goes through the thing. So like it's like the convex, so it's slow here, ends up, and then it bends up even down.
I think it's gonna be
Like that.
like the amount of time
That's
it's
just how
gonna
I
take is
think about
less
it.
than the actual.
Yeah, I'm just gonna base everything off of these diagrams.
So it's just like when you look at a mirror.
Oh yeah, can I check
Oh, yeah, yeah.
Can you send me what you have for this sheet tomorrow? I don't know. I copy it down.
Basically nothing. Don't ask.
Oh,
Rather, I was asleep, basically. As I like to say, I was drunk on lack of sleep.
the light is going like this.
I don't know why I like to say it like that, but I
And I could go, wow.
They jam so
This
frequently.
because
Like, I hate that it does. Okay, well, I guess that doesn't, that's not
I can't put like a
like thinking of this now.
on the back side of it and project that.
I still don't like it, but like.
So that's why the trophy
Penny for eraser.
It's just like this.
I don't like it.
Because it's still going together.
Andrew's working on this.
That's gonna pull the
It's scary.
you're spinning it.
Cause that, all that does
your
is.
eyeball, so your eyeball is trying to trace back where that came like your eyeball. These lines.
That was the problem. I
I
want to
can't
you
take it. What I'm going to do is look like it's on the other side. You gotta let those things look small.
You wanna do that? No, you don't. Why can't we use this?
All right, kids, good luck. Oh, yeah.
Papers left to make sure that I don't die while I'm trying to go to sleep.
Thanks.
Gonna be honest, I